Hello everyone. Today we are going to look into the goodness of fit of a regression model. What do we mean by goodness of fit? The symbol used for goodness of fit is small r square for a two-variable regression model. By two-variable regression model, I mean something like yi is equal to beta 1 hat plus beta 2 hat xi plus ui hat. Remember, the goodness of fit is being defined for the sample that we have at hand. Capital R square is the same concept of goodness of fit, but for a multivariable regression model. By multivariable, what I mean is a case where you have one dependent variable yi and many independent or explanatory variables x1, x2, x3 and so on. So what is goodness of fit? Goodness of fit means how well the estimated regression line fits the actual data. So how well does the estimated regression line explain the observed values of yi? Now we can understand this concept using something very basic, our basic tool of Venn diagrams. We have used Venn diagrams to study set theory. So here in the next slide, the circle y represents variations in the variable y, our dependent variable y. The circle x represents variations in the independent or explanatory variable x. Now, every time the x and y circles overlap, the intersection region represents how much of the variations in y are being explained by variations in the independent variable x. So obviously, when we want a good fit, we are saying that a large portion of the variations in y is being explained by variations in x. So we want a large area of overlap, right? So greater the intersection region or greater the extent of overlapping between y and x, the more good the fit is, or the more efficiently or the more properly or the more better that our regression line is explaining the variations in y. So as you can see, the two extreme points or the limits of our value of r square are represented by diagram A and diagram F. In diagram A, x and y do not intersect at all. That means variations in x do not explain variations in observed y at all. So you are talking about r square equal to 0. And F represents the other extreme where y and x entirely coincide. That is, all the 100% of the variations in y are being explained by variations in x. So you're talking about a perfect fit of the regression line. So this r square is nothing but a numerical measure of the extent of the overlap, right? So as the overlap increases, as the area of intersection between x and y increases, my r square value is also increasing, right? So now we can actually derive the value or the formula for r square. So please have a look at this. My original regression line can be written as, okay, once again. My original regression line can be written as yi is equal to yi hat plus ui hat. right? I hope you remember the symbols. Yi is the observed y value. Yi hat is the estimated y value based on the regression values of beta 1 hat and beta 2 hat that we have found out. And ui hat is the deviation between the observed value and the estimated value of y. Ui hat is called the error term, the disturbance term, the deviation of observed value from the estimated value, and so many other things. Right? Now we can write the same equation in its deviation form. So remember, when I'm talking about deviation here, I mean deviation from its mean value. How do I do that? I actually subtract y bar from both sides of the equation. Right? So now this, when I'm subtracting y bar from both the sides, capital Yi minus y bar is nothing but small yi, that is deviations of observed yi from its mean, and capital Yi hat minus y bar can be written as yi hat plus ui hat. Now this is the same equation in it's called deviation form, right? Now, do you remember what the term variation means? It is the sum of square of deviations. And when I say deviations, I mean deviation from the mean value. So variation is sum of square of deviations from the mean value. That means yi minus y bar, the whole square, is my variation in observed yi. Yi hat minus y bar, if I take its whole square and I sum it up, then that will be the variation in the observed yi, and so on. So I need to get the term square on the deviation. To do that, I am taking square on both sides. So taking squares on both sides. I have got, okay, sorry, that's yi square is equal to yi hat plus ui hat whole square. So I can write that as yi square is equal to yi hat square plus ui hat square plus 2 times yi hat ui hat. So a plus b whole square is equal to a square plus b square plus 2ab. That's the formula that I have used for expanding on the right hand side. Now again, going back, what is variation? Variation is the sum of deviations squared. So I need to find the sum of these squared deviations. So how do I find the sum? Let me summing up on both sides. Summing up on both sides, I will get that as summation yi square is equal to, I am applying summation to the entire equation on the right hand side. So each term will get summed up. Summation yi hat square plus summation ui hat squared plus, since 2 is a constant coefficient, I can take it outside the summation sign, 2 times summation yi hat ui hat. So I hope this much is clear. Now, if you remember, we had studied the numerical properties of estimating the regression line using the OLS criterion. So if you remember, I think the fourth I think it was fourth. I don't remember if it was fourth or fifth. The last criteria or the last numerical property of the OLS regression line was that yi and ui are uncorrelated. So if yi and ui are uncorrelated, sorry, not yi hat, the predicted yi. So yi hat and ui hat are uncorrelated. So if these are uncorrelated, summation yi hat ui hat, that is the last term in my equation, if they are correlated, it will be equal to 0. That is summation yi hat ui hat is equal to 0. I'm not going into the proof here because we had a face-to-face lecture where I had derived this fact that summation yi hat ui hat is equal to 0. So using the numerical property, I'm saying that the last term of this equation becomes equal to 0. So what does that mean? I am saying that this is the relation that we are interested in. That is, the sum of variations in observed yi is equal to the sum of variations in estimated yi plus the sum of variations in ui. So this is the relation that I'm interested in. So rewriting what I derived, I had got summation yi square is equal to summation yi hat square plus summation ui hat square. Now if you remember, capital yi hat or the estimated yi is beta 1 hat plus beta 2 hat xi. So if I am subtracting the mean value, beta 1 hat plus beta 2 hat xi, minus, one second. Yeah, 1 second. Minus y bar. So, great. 1 second, I'm so sorry. I need to erase this part. I'm so sorry. Let me just repeat that. So, basically, this can be written as summation yi square is equal to, now summation yi hat square, that is small yi hat, can be written as beta 2 hat squared summation small xi square plus summation ui hat square. Now this term summation yi hat square is the variation in observed yi. I'm calling it the total sum of squares, right? Summation yi hat square, which can also be written as beta 2 hat square summation xi square, this is my explained sum of squares. In other words, it is how much of the variations in observed yi is being explained by variations in xi, or the independent variable. And what remains is the residual sum of squares, which is the portion of the variations in observed yi which is not being explained by variations in independent variable xi. It is from here that we say that TSS is equal to ESS plus RSS. Right? And if I divide both sides by TSS, since I'm dividing both sides by TSS, what I get is 1 is equal to ESS, the ratio of explained sum of squares to total sum of squares is what I term as R square, small r square, because here we are talking about a two variable regression model. Plus, I can write this as ui hat square, summation ui hat square divided by TSS, or I can write this as 1 is equal to R square plus residual sum of squares by TSS. You can use either of this. You can use either of these equations interchangeably. So I hope this is clear to you. If you have any doubts in this derivation, you can look into chapter 3 of the book. I believe I have explained all the missing steps, and if you have any doubts, please get back to me. So moving on. So from the regression function, we get the relation total sum of squares is equal to ESS, explained sum of squares. Explained sum of squares is nothing but the variations in the estimated values of y about its mean plus residual sum of squares, which is sigma ui square, ui hat square. Once again, there's a hat here. Ui hat square, that is the portion of the variations in observed y values which has not been explained by variations in the x values or my independent values. So here we have again that R square, which is called the coefficient of determination, is the explained sum of squares divided by the total sum of squares. Now, two important properties of R square. Firstly, it's a non-negative quantity. The fact that this is sum of squares can never be negative, that itself should give you an idea or a hint that R square cannot be negative. What are the limits of R square? I had shown it to you with the Venn diagram. The limits of R square are 0 and 1. So R square will always lie between 0 and 1. 0 means not even a tiny bit of the variations in observed y is being explained by the variations in x values. And 1 would mean that all or the entire 100% of the variations in y values are being explained by the variations in independent values, independent variable x. Right? That's a perfect fit. Now, another formula that can be derived for R square is summation xi yi summation xi yi whole square. One second. Once again, that is, it's like this. Summation xi yi the whole square divided by summation xi square summation yi square. Now, this formula should look very familiar to you. It is because the square root of this is nothing but what you have learned in your statistics classes as the coefficient of correlation, right? So the derivation of this formula of r square from the above equation has not really been shown right now because it's not that important. The derivation is there even in your book. So if you have any doubt over there, please get in touch with me. Just remember this, that your coefficient of correlation whole squared is the same as your coefficient of determination r square in the two variable regression model. Now, often you get a question between differences between coefficient of determination r square and the coefficient of correlation r. Mathematically speaking, r coefficient of correlation is just the square root of r square. Whether it is positive or negative will actually depend on the sign of the covariance of the two variables under consideration. But conceptually there are many more differences. Coefficient of correlation r is a measure of linear association between the two variables x and y. Because it is a measure of linear association, it can be positive or it may be negative. Its limits are different from r square. It varies from -1 to 1. And we have discussed this earlier also. Correlation is symmetric in nature. Now, symmetric in nature means two things. First is that coefficient of correlation between the variables x and y, that is r xy, will be the same as coefficient of variation between y and x, that is r yx. It also means that both these variables are being treated similarly. Both these variables are being treated as stochastic variables. Recollect that I have already discussed this in the introduction to regression models. Okay. For more details, you can go back to the slides that I have uploaded earlier. Another important property of coefficient of correlation r is that it is independent of changes in origin and scale. So if we have two variables x and y, and we know its coefficient of correlation rxy, any transformations of variable x such as x star and variable y such as y star. Look at how I have transformed it. X star is ax plus b. When I multiply x with a factor a, I am changing its scale. And when I add a constant b to it, I am changing the origin of the variable. So the same operation has also been done with y. I have multiplied by c and added d to it. So I have changed its scale as well as its origin to get the new variable y star. So even after transformations of origin and scale to the original variables, if I check or calculate the coefficient of correlation between x star and y star, it will be same as the coefficient of correlation between x and y. So the coefficient of correlation will be equal to rxy. This is another property of r. Often you get this question of comparing coefficient of determination with the coefficient of correlation. Remember to mention that the properties are different, the meanings are different, and also the uses of it are different. Moving on to the next property of R. You should remember that if x and y are statistically independent, here the spelling of there should be THEIR. right? If the two variables x and y are statistically independent, their coefficient of correlation will be equal to 0. However, the reverse or the converse need not always hold true. Just because the coefficient of correlation is 0 need not necessarily mean that the two variables are independent. If you want an example, something like a relation y equals to x square. In this relation, y and x are very much related to each other, but the relationship is not linear. And my variable r, or the coefficient of correlation, can only detect and measure linear association. So if you actually have variable y which is equal to x square, then the r for x and y will be 0 or near about 0. But they are not at all independent. In fact, they are very much dependent, right? Just remember this example of y equals to x square to understand this fifth property of R. Finally, what we had discussed even in the beginning introduction lectures, linear association or dependence as measured by the coefficient of correlation does not imply a cause and effect relationship. On the other hand, when we are estimating a regression model, we are in essence implying that changes in x cause or affect changes in y, right? So that's a very important difference between correlation and regression. Okay, and finally, also note that R square has another possible formula, which is the squared coefficient of correlation between observed yi and estimated yi, that is observed yi and yi hat, right? Just remember the basic formulas. The derivations do not always come except for the ESS and TSS. TSS equal to ESS plus RSS part, which is why that is the only one that I have discussed with you. Sorry. And that's it. So that's it for today. With this, I have actually finished the third chapter of the book that I have uploaded of Damodar Gujarati. So what I now want you to do is to keep all these lectures in mind and go through all these PowerPoint presentations and proofs that I have uploaded. And please read from chapter 1 to chapter 3 without skipping anything. And I want you to get back to me with any doubts that you have, because this is basically the foundation part of your econometrics, right? From here on, we'll be moving on to a multivariable regression model. But if your two-variable regression model is pretty much clear conceptually, you will find all the rest of it simple. It's simply an extension of the two-variable regression model. Thank you.